Hey, calculus students. Uh, Welcome to this extra example video on evaluating a definite integral with integration by parts. We already did one indefinite integral in class, but I thought it would be great to show you another one. So we're going to be evaluating the integral from 0 to 1 of arctangent x dx. Now, you look at this and other than the fact that it says on the screen there, do this with integration by parts, what would make you think of doing integration by parts with this one? Well, our integrand is the arctangent function. It is one of our 13 basic functions of calculus, but it's not one that is on our list of basic antiderivatives. So we don't have a quick and easy way to do this one. And arctangent is a relatively complicated function. However, you may recall the derivative of arctangent and that it gets quite a bit simpler. Its derivative is 1 over 1 plus x squared. That's quite a bit simpler, maybe easier to work with for integrating purposes. So if we take u to be arctangent, we have, I think, a lot of promise there in terms of getting an integral that's going to be simpler to do. So let's do that. Let's, that wasn't supposed to show up yet. U to be arctangent x, and let's also take v, then will be what's left, which in our dv is just going to be dx in this case, as it has to be since that's the only thing left. Okay, well then du in this situation will be, as mentioned, 1 over 1 plus x squared dx, promising because it's simpler, and v will just be x. Let's see if I can get that a little cleaner. Okay, so let's apply the integration by parts formula and rewrite our integral. So uv, we're going to have, I'm going to put the x first, x tangent inverse of x. And now remember, the key really to applying integration by parts to definite integrals, the new key, I guess, beyond what we already had as keys, is remembering to evaluate that first term at the limits of integration. And then we have minus the integral, also still with those same limits of integration, v du, so we're going to have x in there. Du, we've got 1 over 1 plus x squared, so I'll just put that 1 over 1 plus x squared, or that 1 plus x squared in the denominator, and then we multiply by dx. Okay, so there's our new integral. And if we look at that new integral, just kind of take it at face value there. You say, yeah, this is an integral that I know how to do. It's not an automatic one. It's going to require substitution. All right, so now we get to continue on here, our integrating quest, with another technique of integration. And this time I'm not going to use u, as is often the tradition with substitution. Because we already used u, it has the potential to get a little bit confusing. So let's use w instead. And let's take w to be 1 plus x squared. We see something very much like its derivative appearing as a factor in our integrand. And in fact, dw is going to be 2x dx. The one term goes away when you differentiate. And we really like to have just x dx, so let's divide both sides by 2 and get that dw over 2 equals x dx, and we see that right in our integrand, which is great. Now, this being a definite integral, again, with substitution, you've got some options. You can leave the limits of integration as is, or you can decide to change them. I'm a little bit of a fan of changing them myself in a situation like this. So I'm going to say when x equals 0, w is equal to 1. You put that into the formula, you get 1. And when x is equal to 1, which is our upper limit of integration, w will equal 1 plus 1, which is 2. All right, let's put this substitution in. And while we're at it, if we want to work in parallel here, we can also be evaluating on that first term a little bit, so let's do that. So if I put 1 in there, I'm going to get 1 times arctangent of 1 minus 0. Well, okay, we'll put this in here. I think you can see what's going to happen with that piece. 0 times tangent inverse of 0 is just going to be 0. Okay, now enacting our substitution, we now have the integral from 1 to 2 in terms of our new variable w of, let's see, x dx becomes dw over 2. Let's just pull that 1/2 out front as a constant multiple right away. And then we got dw. And the 1 plus x squared, of course, that is replaced by w itself. So we get just dw over w. And now this is something that is on our basic list of antiderivatives. Antiderivative of 1 over w is natural log of absolute value of w. The absolute value is not going to be necessary here because our w's lie in the interval 1 to 2. They're positive anyway. So let's proceed. Again, going in parallel here, we can keep simplifying. 1 times tangent inverse of 1 is just going to be tangent inverse of 1, and we should evaluate that. If you want to see if you can remember arctangent of 1, you could pause here and think about what that is. We're trying to figure it out. It is pi over 4. Uh-oh. Okay. Pi over 4 is what we get for that first term. Second term, we already mentioned that's going to be 0. Then we got our 1/2 out here still. Antiderivative, natural log of w. Again, you like to think about putting those absolute values on there, but we don't need them here because we are on a positive w interval anyway. Okay, and now we are getting close. We're just about home free here. We got pi over 4. Evaluating for w here, we do not have to go back to x because we changed our variables. Nice advantage of this approach. We get natural log 2. Whoa, kind of melded my L and N together there. Natural log 2 minus natural log 1. Okay, and natural log 1, you probably remember that one, is 0. So we have pi over 4 minus 1/2 natural log 2. If you wanted to get fancy with this, you could take the 1/2 inside the natural log. It becomes an exponent. That would be a square root of 2, but it's probably simpler as it is. Okay, now, again, the big question to ask yourself when you have done a definite integral using integration by parts is, did we get a number? Okay, because not getting a number would probably indicate you forgot to evaluate part of your result at the limits of integration, but we did get a number, pi over 4 minus 1/2 natural log 2. That is a number. You may wonder, well, yeah, what is it as a decimal? And in some contexts, that may be important to know, but really here in Calculus 2, our focus is on getting exact answers. And so we would want to leave the answer in this form, or at least have it there in this form, even if we're also interested in seeing what that is approximately equal to, which I'll leave it to you to plug that into your calculator and get a decimal approximation. All right, I hope you enjoyed this video, and we'll see you in class soon.